All right, so let's get this thing going. So today, anybody remember what I said we were going to talk about today?
Oh, I looked it up last night because I forgot it was point source arrays.
Point source arrays.
Yeah.
So what in the world do I mean by point source arrays? Well, an array, in the context of loudspeakers, an array usually means multiple loudspeakers that are set up together to reproduce the same signal. Okay, you array them in some sort of way or group or form that where they relay the same sound out to some area of listeners. Why would you want to do that? Anybody? Why would you want to add? Why couldn't you just do it with one?
Sometimes
Cover more area.
Yeah, remember I said last spring in our system design class that the best kind of sound system has how many loudspeakers?
one.
One, right? So the best kind of sound system has one loudspeaker. Why is that? Why do I say the best kind of sound system has one loudspeaker?
It keeps it simple. You can't have any interactions with other speakers if you only have one speaker.
Exactly. So if you only have one loudspeaker, then you don't have to worry about multiple loudspeakers interacting with each other in some sort of destructive way, which they really, really like to do. And so if you only have one loudspeaker, then you only have to worry about the walls interacting with the sound from the loudspeaker in a destructive way, which is usually a lot easier to deal with. So you should shoot for as few loudspeakers as you possibly can and still get the job done. But if that's not possible, then like if you've got your one loudspeaker and you're pointing it at the area and you're realizing either because you predicted it in ease or you are in the room now and you're figuring out, hey, it's not quite covering everywhere that I want, one possible solution to that could be that you would add a second loudspeaker that would also produce the same sound, and you would try to aim the two now in a way that, you know, between the two of them, they would cover the entire area you're looking at. Today, we're going to look at creating point source arrays. And what I mean by point source arrays is you're going to use a point source loudspeaker. Point source loudspeaker as opposed to a line source loudspeaker, because you can do line source arrays as well, which most people call line arrays, but strictly speaking is really line source arrays, which we will talk very briefly about today as part of our little experiment, but not extensively, because line source arrays, at least coupled line source arrays, tend to not be very useful to us for the kinds of things that we do. Coupled line source arrays are really good if you need to make a whole lot of sound and shoot it a really long ways.
You're okay with it doing a lot of things.
Yeah, and you're okay with spending a whole lot of money and being, having, a sound system that's very large and very heavy.
Sounds like a Ryan thing, yeah.
And then you can, and the other advantage of that is you get some directivity, extra directivity at low frequency that you don't normally get with point source loudspeakers, although that is changing. There are some very clever engineers right now that are getting some pretty impressive low frequency pattern control out of point source loudspeakers by doing some very incredible trickery. This is not about line source arrays. We're talking about point source arrays, and we're specifically today going to look at arraying them horizontally because that's easier than arraying them vertically. I do want to set up some rigging in here. By the way, who's the person who's in charge on the day that we were supposed to do our full system tune? Do you remember who volunteered for that? Do I need to look it up?
I think it was Sam, and I think I'm assistant.
Okay.
Yes, I do believe that as well.
Okay, so I need to give you guys a kind of pre-assignment for that day, which is that we need to figure out how to fly something in here.
Are there I-beams?
Yeah.
I mean, I'm looking up above me, and there is truss steel up over here. There are some I-beams holding up the prop storage floor over here.
You could do I-beam clamps.
So.
Yeah, but
So if you guys can go and talk to Dennis.
DGB.
He said that he would be happy to help you think through that and come up with a plan, given that you sat through his rigging class last year.
That's a good class.
Is there a lift down there?
Yeah, how do we get up in the air?
Well, this is part
the
of what
dentist
you need to
question.
figure out.
Yeah.
That is part of the assignment. So I'm telling you this now because it might take a few weeks to get that all figured out. But as part of that, I want to be able to actually fly out a center cluster in the shop here.
Yeah, to height, right?
Yeah, as high up as we can get it.
All 10 feet.
So anyway, that's something you can work on. But so sometimes for a center cluster, like over in the Stevens Center, you might create a vertical point source array, which is what is in the eyebrow at Stevens Center, because the Stevens Center is not particularly wide area to cover, but with the balcony and everything, and just where that eyebrow position is, you're trying to cover, it's got to be like 150 degree, amount of coverage. So we actually have 3 point source loudspeakers arrayed vertically to try to get that coverage. So the same principle applies to the vertical arrays as the horizontal arrays, but the vertical arrays are just harder because it requires trickier rigging. Well, because you sort of basically have to rig them even if you're just experimenting, whereas doing horizontal arrays, I can just set them on a table like this and we can kind of play around and get the general idea. Okay, so any questions so far? Everybody understand more or less what we're trying to accomplish? Okay, so the question for today is that we're trying to answer, there are a few questions. One is that I'm assuming that you will have some way of recognizing that you're not covering the seating area as much as you want, right? We learned how to do that last spring, to predict that using ease software or whatever else you're using. So you should be able to know that long before you go up in the air with your one loudspeaker that's not going to get the job done. So presumably you will make that discovery before you start pulling equipment. But once you make that discovery, then the question is, how do you know what angle to splay them, to get them to do the thing you want them to do? And as we will see in a minute here, you have to be very careful with that, because you can cause a huge mess if you do it wrong. So that's the first question. How do you know what angle to put them? Second question is, how do you know which kind of loudspeaker you can array in a point source array and which kind you can't? Right? Because you can't do this with every kind of loudspeaker and have it really work. So how do you know which ones can make point source arrays and which ones can't? So we've got, Grayson and I pulled several this morning. We're going to try all of them if we have time, and they're all different in some way, and we will see which ones work and which ones don't, and try to figure out why the ones that work and why the ones that don't. So to begin with, let's just measure this loudspeaker. We're starting off here with the D&B Q7. Now, I checked this before class started, and the horns are both rotated the same way. They weren't at the beginning of this morning, but I fixed that. So this is got a directivity horn in it that claims to cover 75 degrees on the horizontal axis and 40 degrees on the vertical axis. Although, as we know, that is a gross oversimplification. But that is generally the working theory we're going to go with. So the first thing you want to do when you're trying to figure out how to do this is you just want to measure the loudspeaker on axis. What does it do all by itself, pointed straight at a microphone or a listener? So yes, Nora, you're doing exactly the right thing. Get it lined up and pointed directly at the mic as much as you can. And we just want to see what this thing does all by itself. So what you're going to do, Grayson, is you're going to turn on the pink noise, and then you're going to turn on the mic to measure. Okay, now the first thing, what's the first thing we want to do now with this kind of a measurement? Do you remember from last week?
I have no idea.
So here's your clues. We've got a really messy phase trace, and we've got really spotty coherence. Do you remember what causes that from last week?
Delay?
Yes. Okay. So there is a certain amount of time.
Oh, so you have to change it
Yes, so there's a certain amount of time that it takes for the sound to come out of Smart, go through the amp, come out of the loudspeaker, travel through the air, get to the mic, and get back into Smart. And you need to account for that time in your measurement. The easiest way to do that is to use that little find button for find delay. Okay, it says that it thinks, well, the measured delay was 7.23 milliseconds, which it thinks is about how many feet? Does that sound reasonable to you?
I think it's probably longer, but it sounds right.
Yeah, I mean, if it's wrong, it would be like really wrong. Like it would say 150 feet. And you'd be like, that's not right. So yes, this sounds reasonable. So go ahead and insert that delay. There we go. Okay, now what we need to do is we need to line up the level between the mic and the reference signal. And there are two ways to do that. The way that we know we need to line it up is that if you look at the 2 meters there under the mic 3, you can see that the green one is coming in at a lower level than the blue one, right? Yep, and then over in the magnitude response there, you can see that our green line is below that 0. That tells us that the measurement signal, which is the mic, is measuring a quieter signal or a lower signal than the reference input, which is the loopback. So we need to either turn down the reference or turn up the measurement. Yes, Grayson, so in front of you, you have some knobs on that Focusrite interface. You should see a knob, a preamp knob for input 8, which is your reference, and input 3, which is your mic. So you need to turn either input 3 up or input 8 down.
I'll try turning input 8 down.
Okay. Very good. Yes, okay, good, stop. Excellent, I'm gonna call that good. All right, so here's what we're gonna do. I'm gonna stop talking. We're gonna count silently in our head to 5, and then Grayson, you're gonna hit the space bar. You ready? I'm stopping talking now. Okay, call this Q7 on axis. Okay, so what we just did, you can turn off the pink noise now for a second. So what we just did is when you hit the space bar, it does a capture function in Smart, where it captures the trace. There's also a button over on the bottom left of the window where you can click and do that, but space bar is easier. You hit space bar and Smart will basically take a picture of the data as it currently stands. Now, it's important to note that this is not an actual recording of the audio. It literally just took, I mean, it's not exactly a picture, but it just captured the line that is currently drawn on the screen.
And it's only in that one instance, right? It's
Exactly.
For a set of time.
It's for that specific moment when Grayson hit the space bar. Okay, and the reason that we did that is we now have a reference that we can use to compare against. Because if we do this right, if we array this right, then these 2 loudspeakers should act like one. And between the 2 of them, we should see this frequency response across both of them, even in the overlap, just for most of the overlap area. So we want to have something to compare that against. Now, the other thing we want to do is we want to find out if there's anything wrong with this loudspeaker before we try to array it. Like, is this what the frequency response of this loudspeaker is supposed to be? Is there something wrong with it? Is there something not wrong with the processing of the amp? How would we know that? Any ideas?
Google.
Can we look at your reference documents for the speaker, like what it is supposed to be able to do and what it's supposed to be able to reflect in
Right.
your primary?
I'd be willing to bet you that the manufacturer who built this thing probably has some
Telling me DMB makes specs?
some information that would suggest what this trace ought to look like, okay? So yeah, you could go and look this up. and find that and see what that trace looks like. So let's go ahead and do that real quick. So Grayson, pull up Safari there on the analysis computer.
Connect to the Wi-Fi then?
Nope, it's plugged in through a wire. So go to dbaudio.com.
Oh, please.
No spaces.
Oh.
No spaces in URLs. dbaudio.com. Excellent. That is the URL for DMB, who made this loudspeaker. Okay, so you're going to go to products, I think. And I think these are technically discontinued. So let's, if you scroll down.
Go to Q series. Oh, wait, there's no Q series.
Yeah, that's what I mean. So, yeah, scroll down in the window there. See, sometimes there's a, yeah, let's see that. Okay, so go to service and support.
Are we just trying to find a spec sheet?
Yeah.
Oh, you can also just Google Q.
So go to downloads. Yes, I know you can just Google it, but I'm trying to teach you to actually go to the source.
Yeah, but when you Google Q7 spec sheet, it takes you to this page, but if you already searched Q7, it will.
So go to, under everything, just type Q.
Q7.
Let's see what we got here. Okay, Q7 manual, that looks good. Let's take a look at what that says.
Oh, please.
It downloaded it, you got it.
Yeah.
Just, it's down there in the download, right next to the trash, you'll see it. Okay, so scroll through that, see if you can find a frequency response for this thing. Okay, that's frequency response of the correction filters that are in the amp. That's not exactly what we're looking for. Hey, there you go. Okay, so let's compare that to what we see in Smart. Yeah, I mean, you're gonna have to kind of use your imagination a little bit, but.
Yes.
I can see it. It counts.
Okay. The point I want you to make, actually bring the one from the manual back, yeah, so we can see the whole thing. Is that flat?
No.
Yeah, I mean, you know,
All is flat.
what a lot of people think is flat is a straight line, okay, for frequency response, and that's just not realistic. This is functionally fairly neutral. I mean, but there's little boosts and cuts and dips and things all through it, and that's just natural. So what you don't want to do is you don't want to like capture it in Smart and go, oh, look at it, we need to flatten this out and spend, you know, a day like fine tuning, you know, 25 parametric EQ bands trying to make this flat thing, because somebody spent a lot of time to build this loudspeaker and tune it and get it all sounding right, and this is how they think it sounded good. So you just want to make sure that what you're measuring is not dramatically different from what they say it should do. And I think at this point, it looks like we're pretty darn close. The only thing I am seeing is, I feel like we're seeing some low frequency roll off.
But that's anticipated.
Well, because there's two graphs there, right? There's one for standard and one for cut, and cut is what you would use with a subwoofer. So let's just make sure that we don't have cut mode turned on this amp. So if we look on the amp, hit the little button there, and yeah, turn it one, click down, hit, and now click on setup. Okay, cut is off, so it should be good. Okay, so that's probably fine. Great, so we've got this now. So now what we want to do is we want to find what we would call the 6 dB down point. The 6 dB down point is how far to the left could I turn this loudspeaker before it gets 6 dB quieter? Because that's the spot where you want the two to overlap, right? Because if you could get the 6 dB down points to overlap in space, and you could get those to be perfectly time aligned in that spot, then what happens when you combine two identical sources in the air perfectly time aligned? What happens as a result of combining those two things?
They would double.
Yes, and what happens when you double it? What happens to the level?
Louder.
How much louder?
By 6 dB.
6 dB, exactly. So if we line up the natural 6 dB down points of the loudspeaker at this overlap point and we perfectly time align them, then they will sum in the air to be 6 dB louder, which just happens to be how much we lost.
And then it's perfect.
And then in between these two, you hopefully get the same thing as on-axis response for a single loudspeaker, right? That's the dream. Let's see if we can pull it off. So how would we know, using SMART, when this thing got 6 dB quieter?
It will tell you. The line will go down by the 6.
Yeah, we would see that green line go down by 6 dB, wouldn't we? I'm going to show you a little trick, a little shortcut that will help you know for sure that you did it. So you see over there on the left, you've got that list of traces, stored traces, and you see the one that you made, that Q7 on axis? Mm-hmm. Click on that, and then select that info button at the bottom of the list. Okay, now you see that thing called dB offset? Mm-hmm. Set that to -6. And hit OK, or apply, yes. Okay, so what it did is it took that little line that it captured.
Oh, so whenever the lines meet.
And it's just drawing it now 6 dB down on the graph than it was when you captured it. So yeah, now all we've got to do is turn this back on, and then you're going to turn the loudspeaker until the lines match. Now here's another little trick. What is going to happen to your measurement when you turn it? Besides the level hopefully dropping, what else will change?
The line shoot itself, like your coherency and your frequency response will change because you're going off axis.
Right, you would expect that the frequency response would probably not be exactly the same, because we know that that's what happens when you go off axis from a loudspeaker. What else will change about your measurement?
Like, just all of them? Like, would your phase get any different?
Yeah, your time will change. Why will your time change?
Delay too.
Because it takes longer to get there.
Well,
Yeah.
Now it's going off to a different place.
Well, just as you move it, the distance between where the sound is coming from and the mic is going to change slightly, right? Yeah. So there are a couple of ways to deal with this. Some people will say, turn it and then try to nudge it to get it so it's the same distance away as it was when it was on axis. That's a valid way to do this, but I find that makes it a little bit more complicated than I think it has to be. So here's a little trick that I do, is I go ahead and turn on something called the delay tracker, okay? And you see that, you can hit that little button that says track next to the find. Don't do it yet. But when you do that, SMART will basically allocate some resources to the computer to constantly kind of measure your delay and keep adjusting it to keep things in time. And you're thinking, gee, why don't we just do that all the time? It's like, well, there are reasons, as you will see in a moment, why we would not want to do that. So, but for now, we're going to turn that on, and then we'll measure this. So you're going to turn on the pink noise, then turn on the delay tracker. And now, Nora, you're going to rotate the loudspeaker to the left until the two lines meet on the magnitude response. Yeah. Okay, stop there. I think you went just a little too far. Very good. Okay, so let's say, I'm going to stop talking for a second, and then let's look at that and we'll capture it. Let's make sure it lines up first though. Okay, yeah, turn it out a little bit more. Yes. Okay, so we're going to count down to 5 and then you're going to hit spacebar. Okay, you're going to call this Q7 off axis. Okay, so now turn off the pink noise. So what do you notice about this that makes you go, So do me a favor, you see the little round green circle next to that mic 3 label? Click that just to turn off the live trace for a second. Okay, so the red one is the actual off-axis measurement that we captured, and the green one is the on-axis measurement displayed 6 dB lower. So any questions about that? Anything about that that makes people wonder what the heck is going on?
Well, like the low frequency doesn't match exactly, but that makes sense because it's less directional. Like that would go off axis and it wouldn't go down as much as these higher frequencies.
Right, so.
Like a perfect.
Yes, this is like, so when, when I said, oh, the manufacturer says this is 75 degrees horizontal and 40 degrees vertical, and I said, that's a gross oversimplification. The reason I said that, don't Google it yet. The reason I said that is a gross oversimplification is that not all the frequencies get 6 dB quieter at that angle.
They're not all that directional.
Because they're not all that, they're not directional in the same way, and it's very difficult to get low frequencies to be directional. It requires a lot of trickery that a lot of times you either can't afford or whatever. There's lots of reasons why, but it's just hard to do. So what you're looking for when you're lining this up is you're looking for that high frequency range. Usually between like 1K and above. 1K and 8K is usually that range where you think you can control pretty consistently. And that is lining up pretty well for us, isn't it? Okay, so the low frequency, we don't need to worry so much about. We know that that's not going to get quieter. We'll deal with that later. We'll deal with that problem later. Okay, so here's what we're going to do. Let's, because Nora nudged it a little bit, let's, we're going to turn the pink noise back on, turn the live trace back on, and just capture a new measurement real quick just to make sure.
We need to unhook.
Yep, so turn that back on, turn the pink noise back on. Okay, so nudge it back into the center, just a tidge. Okay, good, so we can, so now here's what you're gonna wanna do. You wanna now turn off the delay tracker. And just to be super sure, click that find delay button and insert that. There we go. Okay, so now turn off the pink noise for a second. All right, so the reason I turned off the delay tracker is that now what we have to do is we have to hook up that second loudspeaker. Don't do it yet. Wait. We have to hook up that second loudspeaker and we have to get it lined up a perfect mirror image of the first one. And what I mean perfect is the angle needs to be exactly the same, the distance needs to be exactly the same, the level needs to be exactly the same, everything needs to be exactly the same. How will we know when we get it exactly the same?
Lines.
The lines will tell us, okay? The magnitude response line will tell us when we got the 6 dB down point lined up. The phase response trace will tell us when we have it the same distance away from the mic. The phase response is basically a virtual measuring tape we can use, okay? So here's what you want to do, Nora. Without moving the first loudspeaker, you're going to unplug the cable that's plugged into it.
Oh, okay.
And then you're going to plug that cable into the second loudspeaker.
I'm really scared to use it.
There you go. All right, so Grayson, we don't need that on-axis trace anymore. So at least not for now. So you can just click on its little icon, the little green icon next to it, to toggle it off for a minute. Okay, so what we're gonna do is you're gonna turn the pink noise back on, we're gonna leave the delay as is, and it's gonna look wrong. And that's on purpose. So we turn the delay tracker off so that
you can match the delay.
we can match the delay, not by clicking the find delay button, but by moving the loudspeaker.
And then the phase graphs look
Exactly.
correct.
All right, so turn on the pink noise now. Excellent, perfect. Okay, so, all right, turn off the pink noise. Okay, did you all see how that happened? So she turned it and turned it and turned it until both the magnitude line lined up and the phase line lined up. And that way we know that it's both at the same angle, a mirror image is the first one, and it's at the same distance. Because if it was at a different distance, that phase line would change. Okay? So we think we've got this now. Now here's what we want to do. We're going to take your little jumper now, and Grayson, turn on the on-axis stored trace again. If we've done this right, we should be able to turn the pink noise on, and then plug in that second loudspeaker as a daisy chain, and we should see the live trace green line jump up to where the original on-axis line was. Yep, because we should see that 6 dB doubling. So yeah, without moving anything. Now don't do it yet. So we're going to turn on the pink noise first and watch the trace stabilize, and then you're going to plug in the second one and we're going to watch it move, okay? So go for it. Okay, now plug in the second one. Da, 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 da. Okay, so I'm going to stop talking for a second and then turn off the pink noise. Good. Okay. So what we see now is at this overlap, we are now getting, at least at the high frequency, basically the same response that we had pointing at a single cabinet, right? What's the difference we have now, though?
The low end.
Yeah. So what's going on there? What's going on with the low frequencies?
Well, at this point,
They're louder, right?
yeah, like 200 they get louder, and then yeah, it's just like no,
Why are they louder?
because they're omnidirectional learning.
You get
Well-
running into each other and causing.
Yeah, they summed 6 dB as well, right?
Yeah.
But they were not already 6 dB quieter.
So they just gained on top of gain.
Yes.
Based on gain, though.
So this is something that we can use EQ to help us with, okay? So here's what we're gonna do. I think in here I've got an EQ. We can probably try this. Coupling. Okay, so turn on the pink noise real quick, and I'm gonna turn this little filter on and see what happens. See it?
Oh yeah, dude, keep it out. Did you just do like a?
Yeah, so turn off the pink noise. Okay, guys, so what I did is, this is D&B trickery, okay? So they have a little thing in their amp called a coupling filter, CPL. You wanna go back to that spec sheet and look and see what that filter response looks like?
Oh, please.
No, it's
It was open, it's just, there you go. So go 2 pages back up and it'll show you. Okay, so there it is in the bottom. See that frequency response correction of Cpl circuit? Says the Cpl coupling circuit compensates for coupling effects between the cabinets when building closely coupled arrays. It's basically a low shelf, okay? But it's a low shelf that somebody in D&B said,
The low shelf that has a name.
yeah, and it supposedly works really well with these loudspeakers, okay? And you can actually dial in, levels with it. And I just turned it on to whatever the default was, just to see what would happen, and we basically got what we needed. Okay, it just turns down that low frequency a little bit, and now we're good to go. Okay, here's now what I want to try. And this will be tricky, and so we need everybody at home to mute your mics.
Continue muting them.
And then I'm going to mute my mic, and we are going to unmute the mic on Zoom on the analysis thing, and and hopefully you guys will be able to hear this this thing off the mic. So what we want to do is we want to walk across the coverage area of this array now and see how it sounds. Okay, so go ahead and go over to Zoom. Grayson.
Yeah, I'm here.
Okay, and unmute your mic there.
No.
There you go. Okay, good. Yes. So that's good. Now I'm going to mute me.
Can't see it.
Okay. And I'm going to turn this down. Okay. All right. So here's what we're going to do. Turn on the pink noise. And when you guys hear that? Oh, turn on. Can you hear that? Okay, excellent. Here's what we're going to do. I'm going to take the mic and let you hear this. Take turns walking it. So here I am looking straight at one of them, and I'm going to walk across the coverage area, and we want to listen for how smooth it is. Yep. Okay. So now you guys get a chance to do that. Yeah. Everything else right? Okay, so go ahead and turn off pink noise for a second, and then mute that mic, and I'll unmute it. Okay, so what did we notice there as you were going across? And those of you at home can chime in too. What did you notice when you were listened to that coverage area now between the two loudspeakers?
For me, in between, I lost a lot of high end.
Yeah, so there's a little spot. So right here where the mic is, we know it's perfect because Smart has confirmed that, right? But on either side of that, there will always be a little tiny lobe where the high frequency dips out just ever so slightly. And you can't get rid of that. There's no way.
You can also watch it on the thing.
Yeah, you can see it. So you know that happens and you can't get rid of it. It's just one of those things, okay? And what happens is as you go just a little bit to the left and a little bit to the right, your timing has changed a little bit, but your level has not changed dramatically yet. And so they start comb filtering a little bit right there, okay? But then real quickly, you go another 6 inches and that 6 dB roll off starts becoming a 9 dB roll off, and you're getting closer to the on axis of the other one, and that one's getting louder, so the level differential gets pretty big, and so it stops doing that comb filter. So what we're trying to do in this is just minimize that to as the greatest extent possible. So yes, you can just ever so slightly hear that on either side of the mic. Other than that, it sounds pretty smooth, right?
As you move further back, does that little lobe increase?
Ooh, very good question. Yes. And this is why when you do this in real life, you want to have your measurement mic where the ears are actually going to be.
The ears are everywhere.
Okay. Yeah, but you want to have it like in the seats, right? So you pick a spot in the seats where you want to have that be perfect, right? And that's the spot you use to do this. Because if you do it really close like this, and then we flew this up in the air and shot it over in Stevens Center.
It's a totally different experience.
Yeah, it's like by the time it hits the seats, these are not, these 6 dB down points are not like laser beam straight lines. They are, curvy lines. And so you would end up with a bit more overlap at that distance. So yeah, you do kind of want to measure this at the distance you're actually going to do it, just to make it as minimal as possible. I think even if you did it at this distance and hung it like this, it would probably be mostly fine.
Yeah.
But, at a wider distance, you might need to nudge them apart just a little bit more, right?
So is this the thing, like, would you do one measurement at like the back of house and set everything to that? Or would you take multiple measurements and then average everything?
You would do it at the vertical on-axis point of the loudspeaker.
But yeah, like this one.
But like, do I need to be
Middle of the
here?
house, all the way to the back.
It depends on where the on-axis point of the loudspeaker is.
If you draw a line directly out from the horn, wherever that hits the seat.
So yeah, wherever the vertical on-axis point is on the seats, that's where you want to measure from, because that's where you get the perfect frequency response.
Oh, okay.
And then you go horizontally off from there. Okay, now what I want to do is let you hear what this sounds like if you do it wrong, okay? So let me drive this concept home. I'm going to zoom in here to the cabinet so you can all see this. When people are just starting out doing sound like this, they look at these cabinets that are trapezoidal in shape, and they think, oh, I'm going to array them, and you're just going to kind of butt them up against each other, right? So let's do that, okay? And you think, there we go, I've got an array.
That's why they're this shape.
That's why they're that shape, right? If you put no thought into it and just like do this, and there is rigging hardware available that will let you do that.
Is it?
It's a bracket right here, and they like just connect.
There are little pins and stuff to like hold it in that spot, right?
Is that so that way they can like?
They sit like that. Like,
Linear?
like that.
Well, it's because there are, well, we'll get into the reason why later, but there is a way that this becomes very easy. Okay, so here's what we're going to do. We're going to turn on the pink noise, and we're going to do the same thing I'm going to mute here, you unmute over there, and then we're all going to listen to what this sounds like, okay? So here we go. I'm going to move the mic now, and you can hear what this sounds like. Okay, now you guys can take it. And then mute your mic over there on Zoom. Okay, so what did we notice that time?
Worse.
Worse how? Anybody at home? What did you notice that was worse? Anybody?
Dip. IDK.
Well, that's just because I moved the mic, but when you were hearing it, when I was walking across that whole thing, what did that sound like?
Comb filtering.
Yeah.
A lot like home filter.
Because that's what it was, right? You were hearing comb. It was going, you were hearing this, right? As it, filtered out all those high frequencies and swiped them out because these are overlapped too much, but not sitting in the exact same spot and point of space and time, and therefore they were interacting in very destructive ways. So you get that, first of all, right? You get comb filtering, but the other thing you get is this, it's also louder in the overlap, right? So it was both sounded bad and it was louder.
Bad coherency and loud.
You made bad sound and then you made it really loud, okay? And that'll get you every time. So don't do that. Just the shape of the box very rarely corresponds to the correct angle to array the loudspeaker, okay? All right, any questions so far about that? Because this was the easy one. So anybody not understanding what's going on?
Will you zoom the camera back out so we can see everything again?
You don't like my dancing?
Yes.
Thanks.
Any other questions?
You've been cut off.
No one.
There we go, now they can see. Everybody understand what just happened? And what we just tried to do? Okay, so here's the next one I want to try. We have sitting next to the table here 2 loudspeakers that look exactly the same as the 2 we just arrayed. So let's try to array these new ones. We're going to do the exact same process, but with 2 different ones.
Nora, do you want help moving stuff out?
Yeah, someone busted the handle off that one.
I busted it. Thanks for awakening.
Nice.
These things aren't structured.
Okay, no, they're not. Okay, what's the point?
Sure, no. Should I start with just one on axis again?
Yep, so we're gonna do the exact same process. So tell me, Nora, I'll look on the back of that thing. What does it say that this is?
Q1.
A DMB Q1 as opposed to a DMB Q7, okay? But they look exactly the same. The cabinet is exactly the same. So what we need to do is go into the amp there, Grayson, and let's dial in Q1. Turn off that coupling filter and change it to Q1 instead of Q7. That'll make sure we have all the right settings. All right, so we have no coupling and Q1 settings, right?
Did you turn off the Cpl?
Got it? Yep. Okay, great. So yes, now Nora, line this up with the mic. I don't know how to point it to be good. Okay, so let's go ahead and delete all those stored traces. We don't need those anymore. Great, you can delete those other 2. I don't know what those are. Somebody else who didn't delete their stuff when they were done. Okay, so what was the first thing we did?
Delete. Well, enable it and then delete.
Yes. So turn on the pink noise and let's find our delay. Whoa, what just happened?
I haven't done anything yet.
It did get louder. Why did it get louder?
Minorly move the mic and like actually be louder.
I'm out here for
Okay, turn the pink noise back on, and I'll just reduce it this way. Oh, there it goes. That was strange. I don't know. Okay, it's fine. All right, so find delay. Wow, you totally nailed it. Like you put it in just the right spot. Okay, so what was the next thing we did?
Level. Right?
Yeah, which actually look pretty good right now. Yeah, and then we store the trace. So I'm going to stop talking, we count 5, and then store the trace. Okay, so what was the next thing we did? Turn off the pink noise, and now what?
Track on. Put track on and move it.
Yeah, but before we do that, what do we need to do with our stored trace?
Turn it 6 dB.
Yes, so let's now display this stored trace 6 dB down. Excellent. Okay, so yes, now turn on the pink noise and then turn on the delay tracker and see if you can match that line, Nora.
There's the Q1. It's just not good.
Yeah, what's happening?
We lost our high end entirely.
So take it back to on axis and let's watch what happens. Okay, and now try to find it again. Okay, good. All right, turn off pink noise. Okay, what's going on here?
So
It's not working, but what is happening? What do we see happening here?
the high end is getting completely taken out from like 4K up.
Yeah, so it starts out and you can get like the really high frequency to line up, and just as it lines up and you keep going, that highest frequency keeps getting quieter. And it's like this diagonal line, it keeps like slowly sweeping, right? It's not like the one we had before where the whole high frequency range from 1K and above dropped down together, okay? The reason for that is that this loudspeaker has a completely different horn in it, okay? The Q7 has a horn, it's called a constant directivity horn. And it is a directivity horn that is designed specifically to create constant directivity across that high frequency spectrum, so that when you turn it, all the frequencies go down the same. It's designed to do that. It's very, very clever engineering that goes into that. This cabinet has the exact same drivers in it, the exact same cabinet, but it has a different horn. And I'm going to see if I can let people at home see this horn as well. It looks the same. Okay, so let me zoom in here. Actually, yeah, get one of the Q7s out and let's put it right next to it. And then we can see both of them. You can take the foam off and let's look at the two. Okay, so aside from the little sticker that tells you the directivity, and it looks like these horns are maybe rotated a little bit, right? Other than that, from the outside, they look mostly the same.
But the shape of it is different.
It is a little bit different. Okay, so Nora, stick your hand inside this horn here. Like, go in here and tell me what, if anything, you feel.
There's like a roundness.
There's a little bump in the middle, right?
And then there's like a divot underneath it, so it's like a.
Yeah. So on one side of the horn inside, there's a bump, and then the other side, there's a dip. Put your hand in the other horn. Put your hand, and then wash your hands after you all both touch the same thing.
You feel it? Put your hand in Q7.
You feel the bump and the dip?
Well, see, this is straight.
That's straight, right?
That's a
Hey, come here, I got way too much sand.
Yes. So what is that all about?
No, I don't.
Anybody at home know what that's all about?
Making sure that there's the same amount of time whether the sound's coming out the middle of the horn or the side of the horn.
Right. So this is a horn that is called a, it is a line source horn, okay? So when you're creating, this is not a class about line source arrays. This is a class about point source arrays. So I'm not going to belabor this point too much. But what I am going to say is that when you are creating line arrays have to do a very different thing, okay? And one of the things that line arrays have to do in order to work the way that they work is, yes, what Ryan said is that you want the sound to come out, you know, if you measure a point source array, you would see, and we know this, that, you know, depending on where you are on angle with that horn, we know it gets a little bit quieter or louder depending on where you are. But what else happens is that the distance changes a little bit. Okay, so the sound coming out of the sides of that horn comes out a little bit later than the sound that's coming out of the center of the horn. Okay, and for a line source array, you don't want that. You want it to be coming out at all the same time. So what they've done is they've basically created a longer path for the sound to get through the horn when it travels through the middle by creating that little dip. So that little dip is just in the middle of the horn, but not on the sides of the horn. So the sides go through unimpeded, but the sound that goes through the middle of the horn has to go that extra little distance going through the dip before it comes out.
Like a U-bend in a plate.
Exactly. And so now all the sound comes out at the same time, which is very important for making line source arrays. The other thing that happens with line source arrays is the original line arrays were really just circular drivers, right? That you just made big arrays of boom, 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 boom. And the way that they didn't cone filter is because, as we know, we learned this last year, that circular radiators get more directional the higher you go in frequency, right? They just beam and beam and beam the higher you go. So when we were creating something like this, it has a directivity horn because we want the extra loudness that you get when you slap a horn on a driver, it gets louder. But we still need it to do that same thing that a circular radiator does, where it gets narrower and narrower and narrower. So that's the other thing that happens, is they create the horn in a way that does that. And the reason that you want to do that is so that you can put them straight next to each other and they don't cone filter. Okay? Because as the time changes, they're getting narrower and narrower at higher frequencies and wider at low frequencies, and they stay pretty consistent.
So if we bump these like that?
Yes, so if you bump these like that, and actually you could even do it like this. I mean, you could almost put them.
Oh, just nose to nose.
Yeah. So plug them both together, fire them up, and let's listen to what this sounds like. So I'm going to mute my mic over here. Unmute that mic on yours. And fire for pink noise. And I'll let the people at home hear this. Okay, it's very narrow coverage. Listen to what happens. Yeah. Yeah? Now watch this. I can do this. Tweak it a little bit. It'll still work. Yeah, right? So let me do that for the mic. So I tweaked them to okay. Okay, so what hopefully you all noticed, those of you at home and those of you here, that it doesn't seem to matter what angle I put these at, as long as the front of them are touching, it doesn't cone filter the way the other one did. Right? Did you guys hear that at home? Could you hear that it wasn't cone filtering in that narrow area where the overlap was? Yeah, okay. So you're thinking, gee, why don't we do this all the time? Then we don't have to worry about it.
What if they
Okay.
get a different?
What's the problem? What's the problem that we observed in this scenario?
You lose
moves like really fast.
Yeah, it's really smooth in that overlap, but you go like a foot on either side of this array and it's gone, right? So if we wanted to cover a really, really large area, we would need a whole bunch of these.
We have a whole bunch.
We do have a lot of keys.
We have like, what do
We have 4 of them.
more?
Hey, that's enough.
So we could do 4, which would give us some, but
If you keep going, does it still?
yeah,
Like if you put.
you can just slap as many of those together as you want.
See, that's fine. I want to make a circle.
Now you do then need to, you will have the low frequencies build up. You do need to like do that coupling thing.
It's a full circle and then you put a subwoofer in the middle.
Yeah.
It's my sound system.
So that's one of the advantages of, the other advantages of line arrays is that you can sort of put as many of them together as you want. You don't have to worry a whole lot about how they're going to interact because someone else has already figured that out for you. But to cover the same area, you need a whole truckload of them as opposed to
Like
2 of them like we did,
yeah.
right? So it's very expensive. And there are reasons why that extra expense is worth it, but I would suggest that those reasons almost never apply to most of the stuff that we do in the kinds of shows that we do, okay? So that's as far as I'm gonna get in explaining that line array stuff to you, but if anyone's got any questions, I'm happy to attempt to answer them. Anybody? No? Anybody at home? Anybody here? Okay. Should we try our next option that,
The MS-20.
let's do the, yes, let's do the JF60s. Okay, so the first thing we now know that if you want to create point source arrays, we know that you need loudspeakers that have constant directivity horns, right? We just learned about that as opposed to line source directivity horns.
No, is it an everywhere thing or just a DMB thing?
That's an everywhere thing.
Okay.
Every manufacturer has created their own little way of creating that extra long path through the middle of the horn. And then they patent it, and then someone else, the other manufacturer has to figure out a different way of doing it. But it's all basically the same idea. You're trying to make the sound in the middle of the horn take longer to get out than the sound from the side.
DMB talked about this when we were at the, when we were there.
Yeah, when we were out, he talked about all the different ways of doing it. They actually had graphs of how they all work and diagrams and stuff, which is kind of cool. Okay, so these ones we're doing right now are EAW JF60s. Fabulous little loudspeakers. They make a decent amount of sound for a pretty small package. So the one thing you would want to make sure you do, Nora, is you have a high frequency and a low frequency in these. You want to make sure they're lined up. Okay, very good.
Oh, like, yeah.
So that like both of them are pointing up, right? The other thing I'm going to do is because they're a little bit lower. Actually, this is almost perfect. Okay, so you want to line the mic up with the high frequency because we know that's where we have the directivity. So yeah, let's do this process now for the JS60 and see what we can do. Well, yes, let's change the amp to linear mode so it turns off all of the fancy DMV processing for their stuff. That just putting in a linear mode means it's just a regular amp now.
Yeah. Is it in setup or?
It's the same place where you dialed in Q7 versus Q1.
Okay.
There's an option for linear. So EAW has to make it sound good regardless of which amp you use. So they have to put a lot of passive processing into the cabinet itself. Great. Okay, so we're gonna do this exact same thing again. So we're gonna turn on the pink noise. We're gonna measure our delay. Well, that doesn't sound right, does it? Oh, maybe it's because we're off axis. Let's make sure we're really in the right mode here. Mode. Yeah, it's right. Okay, so we're just going to test both of them first before we try to do this. So find your delay. Yep. Very strange dip going on there, isn't there? So turn up the pink noise a little bit. So just where it says minus 30 dB.
Oh, I'm sorry. Here?
Yeah, just because these are quieter cabinets. Yeah, keep going. And yeah, now turn down the reference input a little bit. Okay, yeah, so see that big dip there at 4K? That's what we're hearing too. Let's let the people at home hear that. Did you unmute there? Okay. You guys hear that? Hopefully with your Sound Gym golden ears, you can hear that dip at 4K. So plug in the other one now. Let's see the difference. That's just like literally unplugged. Let's just A/B them. No, let's do it.
The last one I found that moved NL4 connectors doesn't exist anymore.
It does sound the same.
That's just what they're selling?
Can't be what they're
I think
saying.
so.
Let's look at the spec sheet.
There's no way to apply an EQ in the EPAC, right?
There it is.
Well, that would be on.
Wait, go back, go back. Okay, so keep your zoom in. Just get louder without me doing anything.
I definitely don't have that.
Like something in our amp or interface or something. Okay, turn off the pink noise for a second. Okay, so yeah, let's go look up EAW-JF60. Let's see if this is actually what it's supposed to sound like. I would be surprised if it is, but who knows, maybe.
What did that escape? We were really looking for something that would just give you nothing at 4K. Oh, this spec sheet's.
Oh, there we go. Axial response, there it is. Okay, no dip at 4K, according to EAW. Okay, so let's just to sort of like make sure that we're not doing something incredibly stupid. Let's get this right on the end of the table so we can avoid that, any reflection off of that. Let's get the mic closer. See if we can get a little bit better result here. But I'm wondering if maybe there's like a reflection going on here that's causing some of this. I don't think so.
It's a lot for a reflection.
It is a lot. Okay. Let's try it again.
Wow, now it's louder.
Yeah. All right, turn it off. I'm going to say there's something wrong with our JF60s.
Yeah, there's nothing wrong with the J60s.
I think we've had these for quite some time. I think the crossovers are probably not in good shape. All right,
Okay.
forget about these ones then.
You want to try resetting the amp just in case there's any EQ in it?
Yeah, that was my first.
Well, that's what we tried. I did that.
Oh.
Like a full reset?
Like with
Yeah, I mean,
the on sequence?
Oh, that's a lot.
We can certainly try, but did check it. So, all right, yeah, it's unplugged?
Yeah.
Okay.
If you want to, I put the procedure for it in the chat.
Okay, let's try it again real quick.
Okay. Should be good.
Yep.
Pick noise in 3, 2, 1.
seems strange.
Grayson,
Yeah.
can you find the delay again since it's off now? Like the
Yeah, refind it just to see. I turned down the mic, but number one. Number three. I'm still getting it. Very weird. All right, turn it off. Okay, so I don't know what's going on with those. We'll have to take a look at this a little bit later. So before we completely fire them though, let's just set them aside and let's pull up these ones to see if we get a similar thing. Because that will help us know if there's something going on with the amp or not.
EQ in the cable.
Yeah, probably not, but there might, I mean, might be something in the amp. These are old, these amps are kind of old too, but
Everything's old.
we might be able to get a different amp out if we find we have the same problem. So let's fire one of these up and see what we get.
You want the mic this close?
Yeah, let's just, well, I mean, we can move it. Okay. Go for it.
Tell me when you are ready. Is it plugged in?
Yeah.
Much better. Okay, so turn it off for just a second. All right, so there's grills on these. The first thing I would want to do before I try to array this is I would want to know what's actually going on inside this box. Like, where are the drivers and what do they do? So can we look that up real quick?
Oh. You can't see anything.
What are these fellows called?
JBL MS26. So is there like a picture of the drivers inside or something somewhere?
I'm gonna say no.
Okay, so see if there's like a, go to the owner's manual. It's down there, yeah, down there at the end. There you go.
This one's?
Yep,
Actually?
that's what we had.
Okay.
Fun fact, this is the same document.
Interesting. Okay, so presumably somewhere in here in this thing is a high frequency driver. Somewhere in there is at least one, possibly two low frequency drivers.
One would assume.
Can you just hear it?
So if we turn it on, we could probably just put our ear up against it and listen. So go ahead and turn it on.
Oh, please. You want me to turn it back down to minus 30 dB? That's what was that before?
Looks like a high frequency in the middle.
Yeah.
Would you agree? Okay. Okay, so it's the high frequencies in the middle. That's where we'll point the mic.
Perfect.
Good. Okay, so let's work on our measurement here now. And go ahead and turn let's turn the pink noise up a little bit because these are quieter. A little bit more. Very good. Okay, now turn up your mic input to line this up. Very good. And capture. Well, wait until a second after I've said it.
You said it.
You gotta let the thing, stabilize. There you go. So this is MS26 on axis. Great. So now let's display that 6 dB down. Excellent. Yep, you're going to turn on your delay tracker and turn this on, and now Nora, find the 6 dB down point. Okay. Yeah, okay, turn it off. So what we notice here is that this particular horn is pretty good at being directional for 4K and above, but after that, it's not a very constant directivity horn, and that's just a function of its size, right? In order for it to be directional between like 1K and 4K, it would need to be a little bit bigger. Okay, so generally speaking, you know, even if a loudspeaker has a horn, if it's a very small horn, you may not have a whole lot of success creating these arrays, just because, you know, you can't get consistent directivity across a wide enough high frequency spectrum. So these, I would think, are probably not going to be super successful.
But man, are we gonna find out?
But let's find out anyway.
I just want to double check with something. So you're saying that it's not, or it's very directional from 4K and above?
Well, 4K and above seemed to decay at the same rate.
Yeah.
And so, you know, in fact, we should get Nora to line that up. But then after that, you know, if you wanted to get between 1K and 4K to go, you would have to turn it so much that then 4K and above got too quiet.
Okay.
So let's just line up the 4K and above, since that's the one we know, at least the horn will be consistently directional for. So turn it back on, and then Nora, line that up. Good. Okay, now turn it back on, turn off the delay tracker, and refine delay real quick. Good, okay. So now plug in the other one, and let's find it. No, just with the same cable.
Oh.
Yep. Okay, so here's a little tip. I line up with the active, I shoot it forward, backward, and line up the face. There you go. Good. Okay. So turn off pink noise. Yeah, let's put them both on. Let's. I mean, it's gonna be weird, but we can listen to it
It's gonna
though.
be less weird than those JF60 would have been.
Okay, so fire it up. Turn on your toggle your on-axis trace. Now put it back on again. Okay, turn off pink noise. Okay, so what you see now is that 4K and above summed well back to the on-axis, and then below that we're getting a boost, right? Now we could try to correct for that with an EQ, and we might be able to get something. But let's go ahead and listen to this and just see what it sounds like. Okay, so turn it on, and let's do the zoom thingy. Okay, let me let you guys hear that. Okay. Yeah. Mute your Zoom mic. Okay, so what you notice is, like, that wasn't horrible, right? You didn't hear a massive amount of cone filtering. It was okay. The frequency response, you know, we'd have to tame that low end a little bit, but it was fine. wasn't quite as good as those other ones because, again, we're not lining up as, perfectly as wide of the spectrum, but it's okay. You can do it, it's just not as good. So bigger horns are better for this kind of thing, okay, is the message for this particular experiment. Okay, yes, now, last but not least, let's try these beasties. So we'll move the table, we'll put these in, and we're gonna try these big LA 325s. One. Good. Yep, get the other one over there.
And that way?
Yeah.
3, 2, 1.
Then I can lock it.
There it is. Okay, so let's get this more or less lined up. Good. Let's try it, shall we?
Oh, these have a biamp adjustment.
Correct. Okay, so they do have a biamp switch. So which position do we want that switch to be in?
Mid-high?
What are the options?
Full range faster biamp, yeah.
Full range, yes.
No, full range.
Put it into full range. Because I don't want to get a second amp and a crossover. It's very satisfying. Okay. Okay, so let's see what these things do. And we'll just measure them before I start editorializing them. Okay, go for it. Okay, so turn it off a second. Okay, first thing you notice, wow, they're loud, right? They're a lot louder than those little MS-26s. Okay, so we're gonna need to, let's turn our mic down a little bit. So yeah, turn on pink noise. Now find your delay. Very good. Okay, so yeah, go ahead and cut it. All right, so this is basically the frequency response of this thing. Not bad, right? Not bad. Again, we would want to look that up and verify, but pretty good. Actually, it goes way lower. It stays pretty consistent up to way lower frequencies. It's got some pretty, these are very loud. And, they've got some good power down at the low end. Good. All right, you would expect that out of something this size. The other thing you would expect out of something this size is you would expect, generally, the larger the loudspeaker, the better it is at controlling low frequencies. Mm-hmm. So we might expect that low frequencies would be more directional, perhaps, because of its physical size. So what we should try to do is the same thing. Let's try to see if we can find the 6 dB down point for this thing. So we'll turn it back on. You're going to capture an on-axis trace, display at 6 dB down, yada, yada, yada. You've got the drill now, okay?
Ready?
Dropped again. Why did it drop? I know, like it literally dropped 6 dB. Okay, so turn off pink noise for a second. Okay, so let's display this 6 dB down. I think there's something up with this amp.
This is so much more fun than if there was nothing else with this amp.
Yeah. Okay, so go ahead and, yep, do that, and let's turn it back on. Now, let's see if we can find that down point. That's probably as close as you're gonna get. All right, so capture this. Call this off axis. Okay, so now turn it back on, turn off the delay tracker and refine delay real quick. Yep, insert. Ah, it's like, we got Okay, so now plug in the other one, see if you can find it. See if you can line this up. Turn off the paint. Okay. What about face trace? Fix that. Okay, turn off the pink noise. What's the problem, Nora?
They're big speakers. I can't smush them back.
No, so the problem is, like, you can't get that face trace to line up.
Oh, no, absolutely not.
And there's like no amount of nudging that's gonna make that face trace line up.
No matter.
So I wonder why.
Does it not have anything to do with like the mic being closer to that?
Is it?
It does not have anything to do with the mic being where it is. So let me zoom in on this loudspeaker for those of you at home. And let's see if we can,
Because there's that many freaking drivers.
let's see if we can figure out what might be going on. I don't know how well you guys can see that at home.
Is it because it's like, because it's not like on symmetric thing?
Yeah, so what you notice here is this thing has,
It's because oh yeah, because all
it
the
has a
drivers.
high frequency horn with the compression driver. It has two kind of smaller circular drivers, and then it has two low frequency drivers. But what do you notice about these that makes, Grayson, that makes you go, huh?
It's,
They're zigzags.
so this is where the one is, and that's.
Yeah, like literally none of them are centered.
There's no way to move this speaker and make those drivers line up.
Right, because what's happening is as you turn it, each driver is now a different distance away from the mic. Okay, and the second cabinet is not a mirror image of the other one. So their twin drivers are different distances away, which affects the phase response, okay? So you're never gonna get that phase response to line up. If you call EAW,
What if they were mirror images? Would it work better?
you might have a fighting chance. But if you called EAW and asked them this question, hey, what would be the appropriate splay angle for these things?
They would go, why?
You know what they will say? They will say, get those as far away from each other as you possibly can.
These should not be display arrayed.
They should not be next to each other. They should not be arrayed. They're not designed to do that, okay? So yes, the next kind of rule of thumb for knowing how to make point source arrays is you want to look for something that has the drivers that are lined up on at least the axis, one axis that you can angle them at. If they're not, you're gonna have a really hard time doing this. That overlap is gonna be messy as a result. So if you see cabinets that have, you know, drivers that are all over the place, probably not gonna be able to array those very well.
Why are they like that? Is there like just a general reason, or is it just because like AAW is AAW?
Well, I mean, I think they were, I suspect that they were trying to keep these below a certain height.
And if they lined them up, they would be.
Maybe too tall, yeah. And so that, I suspect that was what was going on.
But there's not anything about doing this that improves the way that they sound necessarily.
No, and what these are designed to do is these are designed to be really loud and just kind of like shoot the sound everywhere.
Deliver sound. Period.
Yep. They're really popular for like DJs who do live parties and dances and stuff like that.
Bands.
They're really popular for like the pop-up live show at the theme park, you know, where you just got to set something up real quick that's really loud, that you don't have to fly, that will sound reasonably good from a good distance away and make a lot of sound, okay?
From what I've seen from all the ones that we've done today, like these ones I feel like have the best, like the magnitude, like the frequency response has been the best overall.
Well, at least it's certainly the low frequency, right? So these go way, you know, these are much more consistent, way down to lower frequencies.
On axis, they're much closer to like a flat response.
Yeah, they're so, you know, they're not bad. I mean, for what they are, they're fine. But they're not something you would want to array. Okay?
Yeah, learned.
So the rules of thumb for creating point source arrays are, you need something that has a constant directivity horn. It needs to be a pretty big constant directivity horn. Teeny ones are harder to do. You can do it with teenier ones, but they're not as good. So big constant directivity horn as opposed to not constant directivity horn, or no horn at all, right? Would be even more difficult. So it needs a horn, and that needs to be a constant directivity horn. The drivers need to line up on that vertical axis so that when you splay them on the horizontal, you can get that phase response to line up. And there's one thing we didn't talk about here, but hopefully what you've seen is that they really ought to be the same, these two loudspeakers.
Oh, yeah.
Right? It is possible, if you read Bob McCarthy's book, he will say it is possible to create something called an asymmetrical point source array. And what he means by that is you can create a point source array using two different point source boxes that have different directivity or different size or whatever. And there's some tricks you can do to do that. I tell you, I have never successfully pulled that off.
When I try it,
I have watched Bob do it a few times, and every time he does it, I just like go, what in the world did he just do? It's tricky, it's very hard. And that's something I think Lance, you did a project last spring where you were trying to do that. You were trying to create asymmetrical arrays. And I was like, it's possible, but it's hard. Much easier if you can, you know, do it with the same cabinet in the whole array. That makes it so much simpler. So that's sort of like a really advanced power user thing that, you know, I know there are situations why you would want to do that or be in a situation where that was necessary, but I do everything in my power to avoid that scenario because it's really tricky. It's really tricky to make that work, make that sound good. But if you want to know more about that, you can read about it in Bob's book. I'm sure there's probably a video on YouTube somewhere of him doing it. But, you know, and Bob, if you're watching or listening at home, you know, you're awesome, and I don't know how you do that. But so that's the last rule is you really probably, at least for now, until you get more experience and get a lot smarter, do these with symmetrical arrays. So the cabinets in the array should be the same, okay? And you want to verify that they are behaving the same way. Just because they have the same label on them and they look the same doesn't necessarily mean they're doing the same thing. And you want,
Where's the JF60s?
yeah, there's, you know, it could be that one of them might have a blown, you know, or a dried out crossover and the other one doesn't, right? So these only work if they are behaving more or less the same as well. So that's something to just verify and watch when you're using Smart, is capturing these traces. Like, do they look like they are the same loudspeaker? Do they sound like they're the same loudspeaker? Because if they don't, you're going to have a hard time arraying them with any level of success. Okay, that's everything I had planned to shout at you today. So any questions from anybody, both home and abroad?
Are we the home or the?
Are we the abroad? Which one's the other?
I think you're the home.
Okay.
Yes, we are home, you are abroad.
Sam, is that a whole boom mic in your frame?
What? Yeah, it's my boom mics right there.
Fancy. So any questions? That made absolute perfect total sense to every single person, and everyone thinks that they could totally do this without me being in the room telling them what to do.
So why don't we do this, like, why don't we use Smart more often? Because I feel like people, I think I've seen it used like twice.
I use Smart all the time.
Okay. No.
And we will almost literally use Smart almost every day of this class. And every student in the program takes this class.
Yeah, but I mean, like, I've been on, X amount of shows, and I would never use Smart for any of the shows.
Yeah,
Right.
and why that is. So that's why I asked, like,
I'm just saying, bro.
we just went through this and we did the same thing over and over again.
Yeah.
So do you think that you could do this by yourself without me standing next to you telling you what to do?
I go home and I write all the instructions.
If you don't think you could do this all by yourself without me, then you should ask some questions right now and make sure we can clarify some stuff. Because this is something you should absolutely totally do. If you are creating arrays like this, you should absolutely totally measure them in the space.
I'm imagining this is like step one. Like, this isn't like you do this and now you're done. Like, is there something that comes after this?
Oh, yes.
So what comes after?
Well, so great. Well, let's go back to the first step where we have the two Q7s. Great. We created now a center cluster. Okay. Is that your whole sound system?
No.
No, probably not, right? You're probably gonna have some other stuff.
Like your game structure.
So you got to figure out gain structure, right? Make sure you're getting, all your level out the right way, so you're getting as much sound as you can out of that. If you have other loudspeakers that are contributing to this, you got to line them up against this cluster in some way, which we will talk about later in the semester. Maybe if this was like a musical or something, you would probably have that center cluster up in the air. You might have some front fills down on the stage. You might have some delay fills in the back of the house. You got to measure all that stuff. You got to line them up just right and get the levels balanced just right. Yeah, absolutely. This is just
step one.
This is one thing. This is how to do one thing. We're going to learn how to do some other things on other days.
Would you recommend, like, doing two Smarts, like doing this Smart here in the shop, like whenever you're building, and then doing another one in space? Or would you just recommend doing one in space?
Well, if you think about it in the shop, what you might want to use this for is just to verify that the loudspeakers work, right? That there's nothing wrong with them, right? That, just like literally fire them up, stick the mic in front of them and measure them and listen to them too.
Yeah.
And just like say, okay, and look up the spec sheet, right? Do just like we did that first thing. Here's what I'm seeing actually happening, or what Smart is telling me is actually happening.
Could you, oh, sorry, I interrupted.
Well, and then just like look at what the manufacturer says it ought to be able to do. And does it look similar? If it doesn't, and if it sounds weird, then try to figure out why.
Dispersion angles are all lies. And we know that.
Well, they're not lies, it's
but
just
like
complicated.
Oversimplification,
Yeah.
and in Spring Awakening, we had a big problem with that on all three of our cluster speakers,
Yeah.
because dispersion angles are all lies. If we had, like, could we in the shop, like, pick up a Q7, like, hang it, and then, like, use a Smart mic to check and be,
Yeah,
what is the actual
absolutely.
dispersion there?
Like just see, like, is this happening? And what you might find, for example, if you realize that you have two of them that are theoretically the same, but you're measuring different dispersion on them,
Then
something's up. And what is probably the thing that is most probably up is that the horn is rotated on one of them. Because like on a Q7, that's not a symmetrical horn. It's a 70 degree by 40 degree, and you can rotate it. And in fact, this morning when we came in and pulled out these Q7s, one of the horns was rotated. They were not the same. And that was the first thing I did is I rotated them. So they were the same. So if you met, yeah, that would be a great thing to measure, is to just see, like, if you know you're going to have to array these in some way, you're not going to array them in the shop because you have to rig them and all that kind of stuff, but you can at least measure them and make sure that they are behaving the way they would need to behave in order for you to array them successfully. And I would highly recommend doing that, absolutely. Other questions?
Hold please while I filter through my brain. My SpongeBobs are going crazy.
But yes, this analysis rack lives here in the shop, right there inside the gate. When it's not there, it's probably out in a theater being used for something, and you absolutely can take it out and use it. It exists for you to use it. It doesn't just exist for me to turn on and
Play with the class.
play with in class.
Is like the focus rate and everything like all a part of it?
Yeah,
Yeah, that
so
whole
it's all one package. You just take it and go.
And the laptop just closes it.
Yep. Okay. You guys at home, how you doing?
Bag comes with it, and that's where the microphone.
Did you hear that? Did you understand all that? Making sense?
Yeah, Grayson's question was one of mine too. It was like, what do we do after this step? So
Yeah, so next week we're going to do front fills. We're going to learn how do you pick a good front fill? How do you figure out how many you need? How do you figure out how far apart they need to be? You know, all that stuff. So who is in charge next week?
Believe it's me.
All right, Elizabeth, so you should check in with me sometime between now and next Friday to figure out what you need to have ready for next
Will you
Friday.
publish that list?
All right.
I know my dates, but I don't remember which one I'm in charge of.
Yeah, I put the first two on Canvas and then I stopped because I had 300 emails that all landed at one time. So
That's right.
yes, I will work on that hopefully today and get the rest of those up there. But I have it. So yes, Elizabeth, talk to me sometime between now and next Friday and figure out what we need to do for front fills so that we can be ready for that.
Perfect.
Okay?
That was graceful.
All right, anything else that we need to talk about?
I think we're good. Not bad.
All right, so we'll sign off from Zoom and then we'll let you two put the rest of this gear away and then we'll be done. Thanks, everybody. See you later.
Thanks,
Thanks,
everybody.
Jason.
Right?